Se llama Antoine Habellion, él es el director de Rockwool, director técnico de Rockwool en América del Norte. Su trabajo se centra en la gestión de proyectos de investigación y diseño de envolventes de edificios relacionados con eficiencia energética, resistencia al fuego, rendimiento acústico, confort en verano, durabilidad y resiliencia. Trabaja con arquitectos, ingenieros y contratistas con experiencia previa en Rockwool en París. Antoine tiene una maestría en ingeniería civil y un posgrado en ciencia de la construcción con una tesis sobre el confort en verano en edificios sin sistema de enfriamiento. ¿Le podemos dar un aplauso?
Thank you. Good afternoon, everyone. I think it's exactly 12, which means we are perfectly on time. I'm super impressed. I'll try to not be responsible for any delays. So as I assume you said, I didn't understand everything, but my name is Antoine Habellion. I'm the technical director for Rockwool North America, and I am by training a building science engineer. So today I would like to, this title is a little complicated, and we've already had some great presentation. We touch on some topics that could have been potentially covered in this presentation. I'm going to focus on very specific aspects of durable, resilient, and high-performance roofing system. Just before doing that, I would like to have a very brief word about Rockwool. So Rockwool is a Danish company. It's a global company with manufacturing facilities all around the world. I think as of today, we're at 51 factories, 4 in North America, 2 in Canada, 2 in the US, and the product that you will see in Mexico will most likely come from our factories in the US. In 2022, we were about 12,000 employees, with sales for the group around 4.1 billion US dollars. And in the past decade, we have been massively investing in North America, which is a fast-growing market for us. So, we've been talking about a lot of different aspects of roofing systems already, and I would like to step back just a little bit and reflecting on all of this, thinking that specifying a roof system is actually not that easy because there's a lot of things that comes into account. Some of these things will be driven by code, obviously, and the things that you'll be looking at will be thermal requirements like R values. There may be, wind uplift resistance, but they might also be about fire, like non-combustibility and so on. Some of these, design choices will have to do and will be driven by serviceability, obviously, like long-term weather resistance, foot traffic, etc. But then there's additional things that, we may want to think about when we are choosing a roof system. And this could be driven by the end user. The end user may require to have a roof that is more performing than what the code is requiring. And in fact, I always like to say that the building code basically tells you what is the minimum legal things you're allowed to build. So by no means building to code is a good, building. And so some of these things may have to do with enhanced thermal efficiency, but also acoustic. I was having a discussion at the break, and someone actually said, oh, Mexico City is a loud city. And I think it's true for all of our big cities, whether it's Mexico or where I come from, Toronto. We live in loud environments, so it's more and more important to think about acoustic. I will come back on this. But then there's also things such as comfort, like the comfort of the occupant. Some of the consideration obviously will have to do with the location of the project, the type of the building. So the conversation about wind uplift is obviously a very good illustration of this. So not the same system makes sense to be used on every buildings everywhere, right? Some location may require systems that are much more advanced, much more expensive to build than other roof systems. And this will be a factor of the type of building, if it's a critical facility, if it's a home, if it's really exposed or not, etc. And finally, and I put it last on purpose, whereas it's probably the first one we all have in mind, will have to do with cost and return on investment as it relates to service life. And so today I will focus on different aspects. The first one is dimensional stability as it relates to durability. So what I mean by durability in the context of this presentation is basically the ability of a roof system to withstand typical loads. So not extreme loads, but typical loads over a long period of time. That period of time will have to be determined. Is it the life of the roofing membrane as declared by the manufacturer? Is it the life of the building? It will depend, but it has to do with normal loads, typical load, what you will expect. And so, re-roofing, roofing investigation, and so on, have shown that, insulation used in roofing system typically moves, right? And they may expand, they may contract. And so if we look at a climate, I guess I will simplify it a bit, but if we look at the climate that we may expect in Mexico, it's going to be a lot of like hot temperatures. And so insulation products may expand as the temperature gets hot. And so what this can do is, if you imagine you have a roof system where all the boards are obviously jointed against each other, as the insulation expands, the boards will be pushing against each other. And as a result, they may actually lift. You can see on the picture, on the top right corner of the slides, you see XPS boards that have lifted from the bottom layer as a result of permanent thermal expansion. And so that deformation is permanent. It's not going to come back into place. And so the problem with these gaps is obviously it could create moisture issues, it will create additional thermal bridging, and so loss of thermal performance, but it could also create stresses on the cover board, on the membrane, and so on, and affect the durability. And so when designing a roof system, it's important to have this kind of consideration in mind. So if we look at dimensional changes of typical insulation product, we'll see that they don't all perform the same. I think from this chart, I know it's probably very small for the people in the back. On the left side, what you're looking at is the dimensional changes in percentage around the length and width of boards. And so on the x-axis, you have the temperature going from minus 20 degrees Celsius to about 80 degrees is where the line stops. And so what you see is, it might seem pretty small, it's in percentage, but typically as we're looking toward the warmer temperatures, typical foam product will expand somewhere between 0 to maybe 0.5, 0.8%. So it's very small percentage. And if you look at the purple line, which is showing EPS, and I think this might be one of the reasons why EPS is definitely not as common on roofing as you will see ISO and XPS, is that you actually see this purple line is dropping past 80 degrees. So why is that? Because past that warmer temperature, there is a dimensional change that is actually unelastic, and so as a result of the warmer temperature and the movement of the product, the insulation is wrapping and is basically breaking down. And so these are things that seems very extreme, and obviously we have to consider this. This is based on selected products. Not all products will be equal, but all products will be demonstrating some sort of behavior of that kind. If you look on the right axis, you're looking at the thickness of the board. Based on the structure of the product, the dimensional changes on the width, length, or thicknesses may be different. So what does it actually mean? So if we look at actual thermal expansion coefficient, again, it's probably very small for people in the back, but I think the key point here is not to see the numbers, is just to see it's actually quite complex. These lines, if you paid attention, they were not perfectly straight, as a relationship between thermal expansion and temperature is not a linear relationship. It actually, if I say it simply, the expansion will increase faster at warmer temperatures than when you're close to room temperature, and it's also true on the colder side. So when you look at this kind of information, which is often communicated by the manufacturer of the product, they will use ranges of temperature with specific coefficient for each ranges that will indicate what kind of movement you may expect. I would like to point out on the chart before that we were getting to 0.5% deformation at 80 degrees Celsius temperature, which I think for a roofing system is obviously expected. Imagine you have a black membrane under the hot sun in the summer, you will definitely have movement. So you need to account for that. And so if you look at this percentage at the size of one board, it's not really much. You may be in the magnitude of 1/4 of an inch of movement. But so you have to think that the bigger your roof is, the more movement you're going to have because each board is going to be moving, and the movement from each board, the expansion in each insulation board is going to add, right? And if you have a very large roof, obviously the expansion of each board is going to be a much bigger problem than if you have a tiny roof where each board will just move a little bit. So this is something that, again, will impact the thermal performance of the roof, its durability, and something that is good to have in mind. Now, if we look at another topic, fire, and I think this is a very self-explanatory picture. I think most of us will know that fires can be extremely severe with very dramatic consequences. This one is an example from a fire in Plainfield, Indiana, from a distribution center in March 2022. The cause of the fire is still under investigation, so it has not been clearly determined what started the fire, but that's a fire that originated from the interior of the building, a content fire, and that fire spread throughout the content and to the roof. And within no time, the whole building was on fire, the whole roof was on fire, and as a matter of fact, there were 350 firefighters fighting this fire for several days. As a result of this fire, As a result of this fire, the building was completely destroyed, complete loss, 1.2 million square feet. It was a facility that employed 2,100 people, and obviously all these people, suddenly did not have a job. And the economic impact on the employees, but also on the company that owned distribution center, as you can imagine, was really, really significant. And so all this to explain with, some very dramatic pictures, obviously fire is a very important matter. So how do you design a fire-safe building? But here, because we're focusing on roofing, how do you make sure you have a very fire-safe roofing system? The easiest way is to look at, Class A assemblies as described by the International Building Code. I know in Mexico it's often referenced and used. And so basically it's, a classification that includes Class A, Class B, Class C, which is determined by, a test that you will do under ASTM E108. And that test will be looking at the performance of a roof system from a fire originating from the outside of the roof. So I was showing an example of a fire in a building where the fire originated from the inside. That test will consider fire originating from the outside. And the idea of this test is basically to see how the roof system will protect the deck and the structure of the building. And so it results in 3 classes. Class A will mean that this roof system is very effective against very severe fire. Class B will be against moderate fire, and Class C against light fire. So I think it's pretty obvious. If you want a fire-safe roofing system, you will want to choose a Class A. Now, this Class A system will only look at exterior fire. And in some of these large facilities, considering interior fire is obviously also critical. And I think the example before was a good illustration of that. And so in that case, whether the building is intended to be FM insured or not, a good piece of information to reference or a good source to look at is to use the FM approvals. And thank you, Melody, for walking us. I don't know where you are, I don't see you, but you walked us in very good detail throughout RoofNav. And I think it was, it's a great introduction to this in the sense that you will basically use these roofing approvals to determine, the different roofing system with different performance. And so in this case, you will be looking at a roof Class 1 system, which will be a roof system that has been tested using a calorimeter test, which is also referenced in FPA 276. And you'll be looking at a roof system that is able to withstand a fire from the inside. And so looking through RoofNav, you will be able to see systems that have been approved that are Class A, Class 1 system, which means that basically if you're using in your project a roof that is Class 1, Class A, you're looking at basically the most fire-resistant roof possible. And so as you lower, Class 1, it's a pass-fail test, so you use a Class 1 or not. But Class A, B, C, obviously if you choose a Class C roofing system, the performance of that roof system in case of a fire is going to be much lower. By the way, I probably should have mentioned it, but so you may notice in my title, I went from durability to resiliency. And there is a meaning between, there is a difference, an obvious difference between durability and resiliency. So I mentioned durability as I proposed that definition. I'm not sure it's an official definition, but the ability of a system to resist typical loads. On the resiliency side, it will be looking at the ability of a system to resist extreme loads, extreme events. And so obviously fire, you don't expect having fire commonly in your building, but that will be an extreme event that you want to make sure, if that happens, and hopefully it doesn't, if that happens, the roof is going to resist the spread of fire, and if possible, the roof will, contribute to increase the fire resilience and the fire resistance of the building. An additional thing that you can look at, which is in approval standard FM 4470, but it's proposed as an optional thing. But another step you can take is to choose products that are described by non-combustible cores. So they're essentially products that are more or less non-combustible. And by taking this extra step, you're adding one layer of resistance, of fire resistance in your system. So, as you can guess, I like stone wool insulation, and stone wool insulation is non-combustible. So it is, for an example, of material that will be, certified as non-combustible core. So again, it's not something that you're necessarily required to do. Even some jurisdiction might require it, but it's more like an extra step you can take to increase as much as possible the fire resistance of a roof assembly. Another thing that you may want to look at from a resiliency standpoint is hail. So Melody also, as she was walking us through RoofNav, she showed us that there was different options with hail going from severe hail to moderate hail to, from severe hail to very severe, okay, I was missing one. Very severe hail to severe hail and to moderate hail. And so on the RoofNav database, when she was selecting she was walking us through the example, we could see there were VSH, SH, and MH hail. And so basically, it's a quantification of the hail resistance of a roofing system. And so essentially, this is done by an actual test where you will be using steel balls that you'll drop on a roofing system and analyze the amount of damage that this steel ball has done. So for moderate hail, you will drop it from a certain height. For severe hail, you will drop it from a higher height. And for very severe hail, you will actually use ice balls that are shown at a certain velocity using a air-powered gun cannon against the roof system and looking at the resistance of the performance of that roof. So how do you identify a roofing system that can meet all these different criteria? When again, I think Melody showed us walk us through the RoofNav in a way that I think help us understanding this, because it is not necessarily really easy as a designer or specifier to pick a roof that you know for sure will meet all these criteria. And so again, whether the building needs to be FM insured or not, using FM RoofNav is a really powerful tool to identify roofing system that will meet these different criteria. So here I just picked kind of a random example. If I remember, Melody said there was 1.1 million different systems out there. And so as you filter throughout the system, you can choose, different decks, different membrane types, different insulation materials, different cover boards, etc. But what you can do is to filter by the different performance criteria that you want to meet. So if you know that you're in a region that is prone to very severe hail, you may set this as one of your key, factor to determine what roof you want to specify. And so the purpose of this table is not really to give you a specific system, it's just to illustrate the fact that there are plenty of systems out there that you can easily find using this database. And that will meet the different criteria. So you could have, you will have your wind uplift requirement. You'll have your fire from the interior and the exterior. You'll have your hail rating and so on. And this is certainly one of the best ways to determine the roof system that makes the most sense on a project. Now I would like to shift away from this type of conversation to something that is maybe a little less common here, even though I certainly have in the past years discussion around acoustic, but I would like to talk about the acoustic performance of roof systems. And before doing this, I would like to step back a bit and just talk about the effect of noise exposure. And so I said earlier in my presentation that we live in louder and louder environment. One of the reasons for this is that we are building denser cities. Our cities are expanding. I know it's my first time in Mexico. I was able to see that here is pretty much similar to Toronto, where the airport is literally surrounded by, commercial buildings, but also residential buildings. And it's very easy to understand that in the case of these very specific buildings that are right around the airport, noise is going to be a very significant source of noise. The airport is going to be a very significant source of noise, but it's not just true for airports, right? It may also be true if you're working on a commercial building that has very loud activities inside the building. You may want to ensure that the noise within the building does not pass through the assemblies and reach the surrounding buildings, but also. And I think this one might be one of the most important one nowadays, is that if you have a building and you have a lot of exterior noise that is able to penetrate that building envelope, you will have things such as health effect, but even more basically in an office building, for instance, you will have loss of productivities because it's difficult to concentrate within a loud, if you're working in a space that is loud. But you may also have an increase of injuries if you have a manufacturing facility where, let's say, it's difficult to hear warning signals from, operating equipment around you and so on. So the effect of noise are very, very severe, very serious, and there are really many different of them that many of them that we can consider, whether it's from the noise to get inside the building, the noise getting out of the building, or the, sound quality within the building itself. And so, I'm not going to have time to cover all the different ways to address all these different potential sources of noise. So for the purpose of that presentation, I'm mainly going to be focusing on noise coming from outside toward the inside of the building. So one very common way, even though we're going to see in a second, it's probably not the best way to do it, but the most common way to assess the acoustic performance of a roof system, or the most common way that is used to assess the performance of a roof system, is to use STC, sound transmission class. So basically, what you will do in this case is you will assess the sound blocking performance of an assembly. So, by the way, I talked about sound, I talked about noise. Maybe I should have started by saying that noise and sound are essentially the same. The difference between sound and noise is that a noise is a sound that you do not want to hear. If we focus on sound now, if you think about a soundtrack, for instance, like a song on the radio, there's obviously in this soundtrack multiple sounds and multiple frequencies. So when we are talking about blocking sound through an assembly, blocking sound flowing through an assembly, what we want to do is to block the sound at multiple frequencies. So when we want to assess the acoustic performance of an assembly, what we will do is we will build a mock-up of that assembly and test it as per ASTM E90. So it's an actual lab test of the assembly where you will be measuring the sound transmission loss at various frequencies. And these frequencies are intended to represent common internal noise. And the word internal is very important here, and that's why I started by saying that even though we use STC as the main metric to quantify the sound performance of a roof system, we probably shouldn't, because that specific metric was designed for interior noises. But we'll come back on this in a second. And so basically what we do is we measure the sound transmission loss at various frequencies, and you end up with very complicated data. You can see on the right side of the slide here, there's a chart, and that chart, I'm not going to walk you through it in this presentation, but basically what it shows is the actual absorption, I should say sound attenuation at these different frequencies. And it's not easy to use for people who are not acousticians. And therefore what the STC rating does, which is calculated as per ASTM E413, is compile that complicated data that consider sound performance at different frequency into a single number rating that makes it easy to compare assemblies. So a typical STC, for instance, will be 45, as opposed to having different numbers at different frequencies. And so this STC number, the higher the numbers, the better. So to give you an idea of that scale, you'll be looking at maybe STC 25 for a single pane window, which is probably the worst performance you can kind of have. Worse will be having a hole in your assembly. But for a common roof system, you probably will be looking at an STC around the 30, 35 range. a better roof system, maybe in the 40-45, and a very good system, 55-60. So that's a scale for a typical roof system. I would say that varies somewhere between 30 and 60. And so what you will do is, as you're deciding what roof you want to use, maybe you use RoofNav to do that, you will then try to, maybe you will have identified 3 roof systems that meet the criteria, from an hail resistance standpoint, from a wind uplift standpoint, it has the right type of deck, the right type of membrane that you want for your project. You could then compare the performance of these different roofing system and see which one has a higher STC. Now, as I said, STC is not the best way to measure or quantify the acoustic performance of roofing system, because what a roofing system needs to do, for the most part, is to block sound originating on the exterior side of the building. And so there is another rating that is called OITC, Outdoor Indoor Transmission Class, and that rating is exactly doing this. So it uses the same ASTM E90 to measure sound transmission loss at different frequencies. However, what it does is that rating, which essentially ends up being the same, a single number rating that you will use to compare roofing system together, what this rating is calculated differently from the STC. And it's calculated in a way that it makes a better representation of exterior noises. And so it's using a frequency range that will be representative of outdoor noise, such as road traffic, airplane, train tracks, and so on. Knowing that this noise tends to be of much lower frequencies than the frequencies from like just people voice, for instance. And this rating ended up being, same thing, single number that you will use. The higher the number, the higher the better. Now the OITC, taking into account lower frequencies, is typically much lower than the STC rating, because for building assemblies, it is much more difficult to block low frequencies. Like typical, building assemblies, they look very thin to low frequencies, wavelength sound, which can very easily travel through. So in order to block, sound of low frequencies, exterior sound, usually the best way is to add mass. So how do you make a roofing system, good from an acoustic standpoint? Well, there's 3 very basic principles that you can apply. The first one is to add mass. So if we consider a very, basic roofing system, we'll have a steel deck, and maybe we'll have some sort of air barrier, and then we'll have some insulation, and then a membrane. That system is very light, right? It's very lightweight. And so one thing you could easily do to increase the performance is to add mass, and a very simple way, very typical way to add mass to a roofing system is to add like a layer of dense deck or some cover boards. Another way to improve the acoustic performance of the roof system is to add absorptive material. And so absorptive materials are typically porous material. And so in a roofing system, that will be, an example will be stone wool insulation. And the reason is because the porous insulation does a good job at absorbing the sound energy because of the change of texture of the material, because as you imagine the air vibrating through the porous material, it's vibrating, it has to go through the air trap between the fibers and then the air and so on. And the structure of the material, which is not homogeneous, makes the sound wave as for effect to absorb the sound energy from the sound waves. And then the last thing you can do is to decouple. And decoupling means remove as many rigid connections that you have between the different layers of the system. So in a roofing system, the most obvious rigid connection you will have will be fasteners. And obviously, you're not just going to remove the fasteners because you want good acoustic, because that's going to have impact on wind uplift performance, for instance. But as you're selecting a roof system, this is definitely something with the acoustic in mind that is very important. So if you have fasteners going all the way through the assemblies, they're going to create rigid connections that are connecting the layer together and which are creating a path for sound to travel through. And so things that you could consider is having an assembly where not all the layers are fastened. Maybe only the bottom insulation and dense deck layers and deck are fastened together, but the top layers, maybe there's a second insulation layer on top of the first layer that is adhered, and then a membrane and cover board that are also adhered. So that's one way to do it. Another way is obviously to do a fully adhered systems where you don't have any fasteners penetrating, but again, it obviously has implication on other things. Another way will be to consider interior finishes. and you could have, drop ceiling with acoustic ceiling tiles, or, I mean, I'm pretty sure this is not exterior space above us, but let's imagine this is an interior, it's a roof right above us. You could imagine having a gypsum finish installed over resilience channels that are hanging from the structure of the roof, and that will obviously decouple the layers again between the most outer layer and the most inner layers. So if we look at some very basic examples here, most manufacturers are going to have plenty of testing. And so, there's a lot of different assemblies out there you can choose from that vary in type of deck, in type of interior finishes, insulation, membranes, cover boards, etc. I just want here to provide a few examples. And I realize it might be very hard to read that in the back of the room, but I'll try to walk you through in a simple manner this example. So if you take a very, very basic system, as I was saying earlier, just a deck, some insulation, and a membrane, you're somewhere in the 30 to 35 type of range. It depends what type of insulation you're using. In this case, we're using 5 inches of fibrous insulation, and so it provides some sort of absorption, so you end up with an STC36. Now, STC36 is really not a great roof from an acoustic standpoint. And so if we want to increase the acoustic performance of roof system, one thing we can do right away is to add some mass, as I was saying. And so if you look at the bottom left example, you'll see that a gypsum cover board was added on top of the insulation, but also some flute fillers in between the corrugation of the deck. And just these two things alone brought the STC to 47. In that specific example, we also mix the insulation type. So there's a layer of stone wool over a layer of polyisoceranurate. What these do is that it first allows us to have a higher thermal performance, but it also allows us to have more insulation with, while reducing the weight on the overall structure. Because of course, adding mass in the roof system is good from an acoustic standpoint, but it's not necessarily good from a cost and structural standpoint, right? So anyway, by just adding a cover board and some flute fillers here, we could bump up the STC performance by 11 points, which is a lot. Adding 3 points of STC, it's almost reducing the sound energy by half. Then the top right corners demonstrate the, what can be done with rigid connection. And so in that case, we have a bottom layer that is fastened, but what you may see is the STC, the two roof system between the bottom left and the top right, they are basically the same. But on the top right, there's actually fasteners. And it's incredible that because the fasteners are actually buried behind the top layers, it doesn't actually have a significant effect on the STC. So if the fastener had been going all the way through the assembly, the STC will have been very significantly impacted. You probably will have lost 4 or 5 points. Whereas in this case, by having only the bottom ISO layer fastened, we can see the STC is unaffected. And then the two assemblies below are just showing again, the effect of adding mass. So in the assembly below, STC49, we added a dense deck layer over the deck under the insulation. And the last assembly, a second layer of dense deck was added on top of the first layer on top of the insulation. And we get to STC53, so that becomes a pretty robust assembly from an acoustic standpoint. So I just want to show some example because these things, sometimes like these are just a few examples, but these things may seem a bit like, very costly or maybe not so common, but there's definitely reasons to do this. This is a very extreme example, but I like to use this example, first of all, because it's very recent, but also because it's quite a unique case. So this is this is basically a project that it's a campus with several sound stages in Yonkers, New York, so more or less in the suburb of New York City. The project is over 1 million square feet, so a pretty big project. And the thing here is they're building sound stages next to train tracks. And so what they're doing in there is filming and recording things while there's trains going by I don't remember the frequency, but pretty much every minute there is a train going there. And so this is the roof system being installed there. And so you can see a steel deck, you can see flute fillers being installed, and then you can see better on the next photo. But you can see they chose to have 3 layers of gypsum, 5/8 on top of the deck, to provide a lot of mass, a lot of sound blocking capacity, and then they needed higher value in this project, so they mixed and they chose to have an hybrid solution using both stone wool for the absorptive properties, sound absorption properties, and ISO for its lightweight properties, but also its higher value. And then they added some layers of gypsum again on top of this, and they ended up with an STC in the 60 range. So very, very high performance roof system. All right, and just to finish off, because we've been talking about high performance, myself and the speakers before. We've talked about wind uplift, acoustic, green roofs, and basically better roofing systems, right? And so one thing I would like to just quickly touch on is that as we are doing this, it's also important to have sustainability in mind. And I know, having conversation with a few of you at the break, it is definitely in Mexico something that is also becoming more and more important. And so I just wanted to give some very basic high-level keys to how to choose more sustainable material. And so I kind of group this into 4 categories. The first one in the environmental impact. The most common way to do this, most basic way, I guess, would be to look at the global warming potential of a material versus another to make an informed decision about which material to use. Then there's a material composition, the transparency, making sure the materials we decide to use do not contain hazardous substances, and that see how transparent the manufacturer of this material is. Are they disclosing the ingredients? Are they hiding the ingredients, or not? Maybe not hiding, but not disclosing. These are things, transparency also, that is important. And one of the reasons why this is important is because it will obviously affect indoor air quality, right? And so that brings me to my third category, which is the occupant comfort. And so in this case, we're looking at using material, if they are used on the interior side of the envelope, maybe with low VOCs, and to look at materials that contribute to thermal comfort, acoustic comfort, safety, etc. And finally, and I know some of the other manufacturers are also very active in this room, are also very active on that topic. The last piece will be about circularity, right? Is the materials that we're using recyclable? Are they able to be recycled, etc.? And so, this can get quite complex. I'm sure some of you have been involved in like LEED projects, for instance. And so, in case of LEED project, these are kind of topic you will have to think about. And one of the most basic way to do this is to look at the global warming potential, which is basically a document that will assess the footprint of a product. And so, more and more products nowadays have this kind of document, whether it's like a generic document for a generic material type, or it could also be like a document that is specific to a material. So in the case of Rockwool, for instance, we have this document specifically for each product that we sell, and so does many other manufacturers. And so that document is called Environmental Product Declaration, and often referred to as EPD. And so, this is, as a specifier, designer, building owner, developer, etc., something that you may want to consider looking at in order to see what is the impact of the material I decide to use, how does one material compare to another, etc. And so these are documents, for instance, if you work on the LEED projects, that will contribute to achieving that certification, because they will give points toward that certification. All right, I'm going to skip this slide, and that's it for me. Thank you very much.
Hello. So a question that we get often is if you need, due to the weight of other insulations like stone wool, rock wool, do you need extra reinforcement in the structural members of the roof? What's your experience with that?
So, there's not a simple answer to this. First of all, because I'm not a structural engineer, and second of all, because there's going to be different scenarios. If you're dealing with a retrofit of an existing building, for instance, there will be certainly limitation to the amount of weight that the existing structure can take. And so, based on this, using Rockwool insulation, especially if you want to have a higher value, will definitely have a very different impact than using a very lightweight polyisocyanurate. And so that's why, in my presentation, as providing illustration, I try to show example of hybrid assemblies, you know, to show that the solution that gets chosen needs to consider, or will always have to consider other things. There's never a simple answer to a problem because everything is you know, is entailed together. So if you're looking at acoustic, for instance, using stone wool insulation is going to contribute to sound absorption and better acoustic, but obviously, you know, if the structure can only carry so much weight, it's not necessarily going to be the greatest solution. Or if there is a very high R value that is targeted, using stone wool insulation alone, which has a high, you know, lower R values than polyisocyanates, may require very thick layers and might not be very practical because of the height of the parapet, etc. So I will say it's something that has to be looked at on a case, you know, by case basis, and probably as a starting point, the R value that is targeted. If there is a high R value, you know, using only stone wool insulation, which is a lot more dense than other foam product, might be much more challenging. If the R value is low, it might be much easier to use on stone wool insulation. Again, there is different factors that needs to be considered.
Thanks so much, Antoine.